While autonomous aerial robot teams can navigate safely, they often struggle to adapt to unforeseen conditions and capture operator intent in unstructured environments. We present a VR-based shared control framework that combines human intuition with robot autonomy. On the left, we show the operator's VR view. On the right, the corresponding real-world experiment with the live operator guiding the system in the background. The user controls the drone through an interactive target, visible in VR, to guide them towards a high-level goal. Here, the operator sees a new obstacle and decides it is safer to avoid passing between. By pulling the target left, the operator influences the planner, which immediately adapts the multi-drone trajectories. After this interaction, the user continues moving the target to guide the team smoothly to the goal. The team here is composed of one real and two simulated drones, but the framework scales to different team sizes and arbitrary obstacle configurations. Next, we introduce the different modules of this framework, each contributing a key element to shared control. We start with the navigation stack. A motion primitive planner generates a continuous path, and the admittance controller combines this path with the user's input to define the team's migration point. Finally, a force-based multi-robot algorithm distributes this command, ensuring the drone follow the migration point while avoiding each other and obstacles. A custom WebSocket interface streams data for VR visualization. In WebXR, the operator sees drones, obstacles, the goal, and the planner's path. They can also move an interactive target, whose updated position is sent in real time back to the admittance controller to guide the drones. The admittance controller ensures that the drone follows the user target while staying close to the computed path for safety. With a basic motion primitive planner, the path would simply be the shortest one, leaving no room for user-preferred path. In the baseline experiment with one real and two simulated drones, this forces the operator to drag the team between two obstacles. As a result, when passing through the gap, the operator must pull harder on the target, causing oscillations, drones moving very close to obstacles, and fluctuating inter-drone distances, a clearly unsafe situation. To enable efficient shared control and give the user more flexibility, we introduced a new cost term to the planner that prioritizes trajectories aligned with the user target. This lets the operator guide drones to fully avoid obstacles, keeping paths smooth and formations safe without extra effort. This approach effectively enhances mixed reality multi-robot teleoperation. It preserves operational assistance at all times, even when the user chooses a path that is more intuitive than the shortest one, leveraging human intuition to explore regions of interest while still progressing toward a high-level goal.